everyone. My name is Alex Leff. Thanks for coming to the probabilistic programming session. We have 5 really cool papers that we're going to hear about today. Starting out with Feras Saad, who's going to be telling us about random variate generation with formal guarantees. Take it away, Feras.
Okay, good morning, everyone. Thanks for the introduction, Alex. This is joint work with Wonyeol, who was my postdoc and who's now a professor here in Korea at POSTECH. So I will start the talk with an overview of random variate generation and the current state of the art in the field and motivate the problem. I'll briefly describe what our technical approach is, present some experimental results, and point to some future work. So in this talk, I'll be discussing probability distributions, and in particular, probability distributions over the real line. These could be continuous probability distributions, things like a Gaussian distribution or an exponential distribution, but they could also be discrete distributions, things like a Poisson or a geometric, but they could also be these sort of mixed type distributions, which are neither purely continuous nor purely discrete, right? So here, you could have a coin flip, and if it comes up heads, you might sample a Poisson, or if it comes up tails, you might sample a Gaussian. So we are agnostic to the actual type of distribution, so long as it is a probability distribution over the real line. Now, of course, there are many other types of distributions. I won't go through all of them, but they have broad applications and many relationships with one another. So, for this session, I don't need to motivate the need for these probability distributions. They have broad applications in many fields. In particular, for probabilistic programming, these are the basic primitives that we use to build complex probabilistic models, right? By composing these distributions to build more complicated simulations. And what I'd like to argue in today's talk is that we need reliable software abstractions and programming interfaces for interacting with these probability distributions, which, for the most part, don't presently exist. So let me just briefly describe what are some of the operations that we want to do with probability distributions. So formally speaking, a probability measure is a set function over the real line, right? So it takes some measurable set A and it returns the probability of that set, which is a number between 0 and 1. The things we would like to do with a probability distribution are maybe sample a random variable, x, according to that distribution. We might want to compute the cumulative probabilities. What's the probability you're between minus infinity and x, or the survival probabilities, what's the probability you're between x and infinity, or you might want to compute the quantiles of a distribution, right? What is the 98th percentile of my distribution of SAT scores, for example. These are the things, some of the key operations that we would like to do. And it's a theorem of mathematics that whether I give you a probability measure, a random variable, a cumulative distribution function, a survival function, or a quantile function, there's a sense in which they are all mathematically equivalent representations of that single probability distribution. And what that means is there are many theoretical relationships that we would expect to hold. So for example, the probability of the left tail, f of x, the cumulative probability, is the probability that your simulated random variable is at least x. Or the survival function is the probability your random variable is greater than x. Or the survival function is 1 minus the cumulative distribution function. This is because probabilities are additive and they sum up to 1. There's the theorem called the inverse transform theorem, which says if I have a random variable x, which is drawn according to my measure mu, that has the same distribution as simulating a uniform number between 0 and 1 and passing it through the quantile function. Okay, and then there's sort of push-forward measures, lots of these different relationships that we would like to hold. Unfortunately, however, in real-world software, because we are computing generally over floating point numbers, not over real numbers, these relationships don't hold. And so here what I'm showing are some functions in the SciPy library in Python, where you have the RV, the CDF, the survival function, and the quantile function, otherwise known as the PPF. And in general, we don't have the relationships that we would expect, because they are computing over floats. The reason is that algorithm developers in the current state of affairs are building their random variate libraries based on the assumptions known as the real RAM model. Okay, so these are very nicely laid out in Luc Devroy's classic textbook, Non-Uniform Random Variate Generation, where you assume your computer can operate freely over reals and do these infinitely precise operations in unit time. Okay, which of course is not very realistic. So for example, let's just consider the GNU scientific library, where we have an exponential distribution over the real line. This numerical CDF x will roughly saturate at 17.3. So if I ask you what's the probability you're less than or equal to 17.3, it will be 1. But if you actually simulate a random variable, it can be as high as 22.18. So there's a clear gap between these two different representations. And the reason is that these floating point functions, x minus 1 and minus log 1p, are not exactly related in any theoretical sense on a finite precision computer. So we did a quick survey of many different libraries, and we found that there are lots of actual issues that people are encountering in practice. Well, an interesting one, for example, was that the geometric distribution in NumPy can actually return negative values. But we all know the geometric distribution is counting the number of coin flips until a success, so that doesn't make any sense. Other things like, on an exponential, you could have a point mass at 0, which on a real RAM, that would never happen, but in a finite machine, that's something you have to worry about. It can give you downstream NANDs. And these are known to cause theoretical problems in areas like differential privacy or cryptography, many applications, some citations on the slide. So of course, the problem here is that, in the real RAM model, all of these representations of a measure are equivalent, but when you perform the numerical approximation, this diagram does not commute, right? So my finite precision implementations don't have any equivalencies that we would have in the real RAM model. So the proposal in our work is to roughly change the type of workflow that we have, which is rather than have a numerical implementation of all of the different functions of a probability measure, what we're going to do is we're going to have a single numerical approximation of the cumulative distribution function, and that will serve as the source of truth for our desired distribution. That's our spec. Once we are equipped with this spec, we will automatically synthesize a random variate generator, or different random variate generators, with different properties, but ultimately all of them will be exact and equivalent to the specified CDF. And from that CDF, I can also get the survival function, the quantile function for free. So we want this very unified representation for our measure rather than this ad hoc one. So how does this work in practice? So here's the interface from the GNU Scientific Library, where I've renamed some of the functions for clarity, but they actually have 4 different algorithms for generating a Gaussian. There's the inverse transform method, the Box-Muller method, the ziggurat method, the ratio method, and they all do different things, right? Because they're all different numerical approximations. The GNU Scientific Library also has 3 different functions for computing the survival probabilities, the cumulative function probabilities, and the quantile, which also don't agree with one another. So I have these 7 different functions, all which do different things. The approach that we're taking here is more of a synthesis type approach. So you can see there on the final 3 lines, we could give the CDF and generate an exact sample from that CDF. Or we can give the survival function and generate a sample from that survival function. And I'll also show it's a very powerful idea, is combining the survival function and the cumulative distribution function to come up with something called the dual distribution function, which is an extended accuracy representation that combines both the CDF and the survival function to represent more values, leveraging some of the limitations and strengths of floating point. But that's the general idea that we have here. So what does this buy us? Let's look at a simple example for the uniform distribution between 0 and 1. The traditional way to simulate a random number between 0 and 1, almost every library does this, is you generate a random integer I, which is between 0 and rand max, and then you'll just divide it, maybe by rand max or rand max plus 1, but this is well known in the literature to have many theoretical and practical problems. You can see clearly there are gaps, you don't get full coverage, and they're also not really uniform probabilities. I have 2 bins over there which have more probability than it seems that they should, right? So there's a paper by Goulart in 2020 which looks at all of the undesirable properties of this baseline generator. Using our approach, what you instead do is you give me the floating point function that defines the CDF that you want. For a uniform distribution, that's just the identity function between 0 and 1. So there's a uniform CDF. I write it in 3 lines of code, and then I generate from that CDF, which gives me full coverage of all the floats with the exact correct probabilities. Now, I will say for this very special distribution, there are many known methods to do it, but what's interesting here is you can do it sort of in a very automated way. And it also generalizes to non-uniform distributions. Okay, so that's a quick illustration. More generally, what are the benefits of the approach? Well, we can automatically synthesize random variate generations given their formal specifications that will all agree with one another. I'll also briefly show that these generators we build are optimal in a very strong sense. They are only consuming the information theoretically least random number of bits to generate an output. So they are actually very efficient in practice. And their distribution matches the formal specification. In terms of the accuracy, I'll also show at the end that we can cover a much broader range of values using our synthesis approach as compared to using the direct approach of implementing random variate generators. Okay, so let me briefly touch on the technical approach. I won't get too into the details, but just give you a high-level overview of what's going on. What we're doing here is we're going to remove the real RAM model, which assumes your entropy source gives you a real number and you transform it to a finite precision model, where your entropy source is giving you unbiased coin flips, and your random variable, your random variate, is a map from some finite string of coin flips to a string x, which is an n-bit string representation of some number. It could be a floating point number, a fixed point number, a posit number, a rational number, as long as it's a finite precision representation of that number. And all of the computations inside the box called random variate will also be finite precision operations. Now, what's really nice about this model is we have a unified representation of any random sampling algorithm in terms of an automata-like structure or a decision tree-like structure called a discrete distribution generating tree. And here's how it works. Suppose I have a discrete distribution over n outcomes, p1 through pn. In this case, it's a fair dice with 6 faces. The algorithm would roughly start at the root, obtain a coin flip. If it's a 0, it goes left. If it's a 1, it goes right. And it keeps repeating this process until it hits a leaf. So that leaf shows you the outcome. And there are some back edges because there's 8 outcomes, but only 6 of them I care about, so there's a little rejection loop here. Right? And you can also express that formally using the syntax of the function f. Right? So this is sort of a general model for any random variate generation algorithm in the random bit model. Now, if I have a DDG tree, the 2 things I care about are what its output distribution. You can simply find that by summing over all the leaves with a given label, multiplying it by the depth of the leaf. And you also care about what is the entropy cost of a distribution, what is the average depth of a leaf, right? Because that's dictating what is the runtime of the algorithm. How many coin flips do I need to hit a given leaf? And so a goal, once you're in this setting, would be for a given distribution, p1 through pn, I'd like to find a DDG tree, t star, that has my output distribution, so it agrees with the given probabilities, and it also has the minimal entropy cost to ensure that it's actually efficient in practice. So there's a general theorem from Knuth and Yau, a classic theorem, which gives a constructive procedure to build an entropy optimal DDG sampler for any list of probabilities, discrete probabilities. The details aren't important, but the key idea is that you write out all of the probabilities in binary, and then you build a tree based on these binary expansions. You put a leaf at a given level only if the bit in that corresponding binary expansion is a 1. So it's a constructive procedure, and so this is basically a solved problem. But it doesn't solve the current problem that we're thinking about today for 2 reasons. The first reason, the challenge, is that even if I have a small number of outcome n, this tree can be exponentially deep. This is something we showed in Popple around 5 years ago. But even more significantly, for the setting we're considering today, I formalized the random variate generator as a distribution over k-bit strings. But if there's 2 to the k of them, right? So if they're floating point strings, there's 2 to the 64 of them. So the number of leaves in the tree will be very large. So it's intractable in these 2 very specific senses. We can't hope to construct the entire tree. So what we do in this work is we introduce a different representation of probability distributions. So you have a CDF, f here, which is a function between 0 and 1. What we're going to do is we're going to change our representation to something called a binary coded probability distribution, which is an alternative representation that maps finite length bit strings to 0 and 1, subject to the property that the probability of the empty string is 1, and the probability of any string b is going to be broken down into the probability of that string followed by 0 plus the probability of that string followed by 1. So roughly what we're doing here is we're representing a hierarchical partition of the real line and representing the probabilities of those partitions. So here's how it works. For the empty string, epsilon equals 0, obviously the measure is 1. For epsilon, for the strings 0 and 1, I've broken the interval in half, and the probabilities of each of those buckets are shown on the y-axis, right? So I can repeat this process to get more and more refined partitions. But what I'm doing is I'm lazily representing the probability distribution, whose probabilities now are shown on the y-axis, right? And so given this particular representation, what I might like to do is sample a string according to these particular probabilities shown on the y-axis, the width of those intervals. Okay, and then I can map any of those strings to an interval of the real line or any point in that interval that represents the outcome, the realized outcome. And what's really nice about this approach is that it also works if I've partitioned the x-axis using any number system. Nobody said it has to be uniformly spaced. They could be floating point numbers, they could be unsigned integers, they could be fixed points, so it's a very general representation for these partitions of the real line. Okay? So obviously a naive baseline to do this is known as conditional bit sampling. You just use the chain rule of probability. You first sample whether you're in the left or the right over here, and then you sample maybe if you're here, you would sample according to these 2 probabilities, etc., just using the chain rule of probability. But this turns out to be highly suboptimal if you implement it in practice. Okay, both in terms of the space, the runtime, and the entropy, and I'll show some comparisons later on. So our first contribution in this work is that we actually give an entropy optimal random variate generator for any binary coded distribution. And I won't go through the details of the algorithm. You can see it's quite short. but it's lazily exploring one of these exponentially sized DTG trees that I mentioned earlier. Okay? And its correctness proof leverages the analytic properties of the real numbers. Okay, so it's quite subtle to get this to work well. And what's also interesting is that it's optimal in 3 senses. It's optimal in space, it's optimal in time, and it's also optimal in terms of the entropy that it consumes. Roughly what it's doing here is it's exploring only a single path down an exponentially sized DTG tree. Right? So it's similar to the chain rule of probability, but it's using a different property based on the binary expansions of the numbers, not on the sequence of conditional probabilities. So at each recursive level, I'm sampling one fresh bit using those lazy expansions. Okay, that's only part of the story, because I started the talk by saying, well, you know, in floating point, we have to be very careful about these issues, right? So here, I might have a CDF on 0, 1, which is x squared. That's a vanilla CDF, because it's increasing and it's monotonic and all that. But if I implement in a floating point, it's actually a discrete function. Right, I only get these black points. I don't get the infinitely precise curve. So what we also do is we give a floating point implementation when the probabilities of this binary coded distribution are floats, not real numbers. And it uses a fast integer arithmetic, and it only uses the same precision as the floating point system. So it only uses, say, 64-bit precision if you're on a 64-bit, if you're representing probabilities using 64-bit numbers. There are some technical challenges that are needed here, like, you know, we need the binary expansions of the difference of a pair of floats, even though that difference itself is not a float. So we need to develop an efficient algorithm for finding these binary expansions using fast integer arithmetic rather than arbitrary precision arithmetic to do this sampling in real time. So those details are in the paper. The final thing I'd like to point to in terms of the contributions is what I showed earlier in the talk based on the idea of combining a survival function and a cumulative distribution function. The idea here is that the probabilities in the floating point range 0, 1 are very precise near 0, but they're not precise near 1. Okay? This is a property of the floats. So if I look at the tail probabilities or the survival probabilities, they're very accurate near 1, but not accurate near 0. So what we can do is we can combine these to come up with what's known as a dual distribution function that's both accurate near 0 and accurate near 1. And maybe, you know, less accurate in the center, but it retains that symmetry. So for example, for the Rayleigh distribution, just, you know, one distribution you may not have heard of, or you may have, if you look at the CDF, it can represent a very small number near 0, but only 8.65. But if you look at the survival function, you can represent a number far from 0, but, you know, 38.6. Combining the two, we can get an extended range based on the idea that you're sort of focusing on the high precision regime. So here's a picture for how this works. You know, you have a cumulative distribution function f, which is increasing, a survival function s, which is decreasing. We find the median, the cutoff point, and we only focus on the probabilities in the lower half and throw away all of the probabilities in the higher, in the lower precision region, which are above half. Okay? And we also show how to do this sampling for a distribution function that combines these two representations. Okay, so I have around 2 minutes left. Let me briefly touch on some experimental results before wrapping up the talk. The 3 questions we're interested in are, in terms of these random variate generators, how are their performance in terms of the bits per variate and their variates per second compared to the GNU scientific library? How accurate are they? And what is the overhead of this extended accuracy method for generation that combines the CDF and the survival function? Okay, so here's a table. Obviously, I won't go through all the details, where I'm comparing the GNU scientific library, the baseline method based on the chain rule of probability and the optimal generator, and roughly in terms of the random bits per variate, where you want lower, you know, we're sort of 3x more optimal than CBS and 142x more efficient than the GNU scientific library. In terms of the samples per second, we are faster by the conditional bit sampling baseline up to 10x, but we're currently a little bit slower, up to sort of a median of 6x, but all the way up to 35x as compared to the GNU scientific library. So there's some opportunity for optimization here. In terms of the accuracy of the generators, here I'm showing what is the width of the interval that you can cover using these different representations, right? So you should basically focus on how wide those colors are. Black is the GSL, and then green would be sort of the best method that we have. And just by visualizing, you can see that the green bars cover many more values as compared to the black bars. So you can cover intervals with a much wider range, up to sort of 10 to the 35x larger. Okay? The final question, which is what is the overhead of this method? Roughly what we're trying to say here is that using a dual distribution function, the overhead is minimal as compared to only using a cumulative distribution function, using the optimal method, because we're not using arbitrary precision arithmetic. We're using finite precision floating point arithmetic, which scales very nicely in this setting. So they work well in practice. Okay, so there's a lot of future work here. I won't touch on everything, but I think there's still some opportunities to do some optimization using parallel or vectorized implementations. We'd like to integrate these primitives as part of an end-to-end verified PPL over floating point numbers, so taking it seriously, not just the primitives, but the whole composition, and doing sort of all these applications in differential privacy and cryptography and other areas that need sort of formal guarantees on the random variate generation. Okay, I'll just close with the contributions and maybe take a question. And there's also a code online if you'd actually like to play with these. So yeah, thanks for your attention, and I'll be happy to answer a question or two.
Yes, we have time for one question. Who has a question?
Cool. So I was trying to compare this to an alternative I had in mind. So if I want to sample from a Gaussian, to use your method, my first step is to write it down as the CDF of the Gaussian that I want to sample. But I was trying to imagine what the alternative would be if I wanted to use, say, the Box-Muller transform, and I could take my Box-Muller transform and change it to use finite-precision arithmetic to get accuracy guarantees. And I was thinking that maybe I could get similar accuracy guarantees, but I would get a really entropy suboptimal sampler. So I suppose my question is, in this context, like how much does this entropy optimality really matter if I want to have like more samples but use?
No, that's a good question. Yeah, I think maybe one distinction here is that if you implement a Box-Muller transform, whether you're using floating point or fixed point, it's going to be intractable to compute the output distribution of that sampler. Because that's a map from, say, the Box-Muller transform has a rejection loop, right? So you would need to map over all 2 to the 64-bit inputs to get a specific output. So you wouldn't have the same guarantees on the output distribution. You wouldn't know what the output distribution is unless you're using sort of very low precision, right? So in general, writing random variate generation code doesn't tell you what the output distribution is unless you're sort of using one low precision uniform number, like maybe 32 bits or 16 bits, et cetera. So I think it's not exactly clear to me what kind of guarantees you would ensure if you're doing pure generation code, rather than synthesizing a sampler that agrees with a given CDF. So I think you will still retain some intractability whether you're in fixed point or floating point. Yeah. Okay, it's your turn now. Thank you. Yeah.